Hello everyone, how are you today? So this day we will be discussing Module 4, Continuity of a Function. Flowing water, long winding roads, and waiting for forever are just examples of uninterrupted actions or continuity. There are times wherein some actions were meant to be disjointed or disconnected somehow. The concept of continuity is also present in calculus. The lesson objectives of this video: first, you are going to illustrate the continuity of a function at a number and an interval. Second, you are going to determine whether a function is continuous at a number or not. Third, you are going to solve problems involving continuity of a function. There are different ways on how we can represent a function. One of those is its graph. If the graph of a function has no gap or holes, then we can say that the function is continuous. Otherwise, it's discontinuous. In addition, a function is said to be continuous at a point x is equal to a if all of the following conditions are satisfied. So there are three conditions that we need to check if the function is continuous or not. First, if f of x is defined, that is, exists at x is equal to a. So a number exists if it is defined. Division by 0 yields to undefined values. The same with square root or negative numbers. Thus, these cases must be checked. Number 2, if the limit of f of x as x approaches to a exists. So based on the previous lessons on limits, so the limit of the function f of x exists if the left-hand limit is equal to the right-hand limit. So that is, so we have this, the limit of f of x as x approaches to a from the left, it should be equal to the limit of f of x as x approaches to a from the right. Third, if the limit of f of x as x approaches to a is equal to f of c. So upon checking whether a function satisfies the first two conditions, check whether the obtained values from these conditions are equal to each other. So if any of the above mentioned conditions failed or violated, of course, we can say that the function is discontinuous. There are different types of discontinuity. So first, removable discontinuity. A function is said to have a removable discontinuity at x is equal to a if the limit of f of x as x approaches to a exists and the limit of f of x as x approaches to a is not equal to f of a. So either because f of a is undefined or the value of f of a differs from the value of the limit according to Comandante 2008. So this is the example of the graph having removable discontinuity. So later on, let's find out how to show unsolved functions having removable discontinuity. Okay, next we have jump discontinuity. The function is said to have a jump discontinuity at x is equal to a if the limit of f of x as x approaches to a from the left is not equal to the limit of f of x as x approaches to a from the right, for a is any positive integer. So this type of discontinuity can usually be found in piecewise function. So this is the example of the graph of a function having jump discontinuity. So this is a piecewise function. And the last one, we have infinite discontinuity. This type of discontinuity exists if a function has one or more infinite limits. Many rational functions exhibit this type of behavior. So this is an example of the graph of functions having infinite discontinuity. So we have f of x is equal to 1 over x. Example number 1. Identify whether the function f of x is equal to x squared plus 5x plus 6 is continuous at x is equal to -1. Justify your answer. For the solution, we are going to check whether the function will satisfy the three conditions for continuity at the given point x is equal to negative 1. So the first condition, f of x is defined that is exists at x equal to a. So the given of our example, we have f of x is equal to x squared plus 5x plus 6 at x is equal to negative 1. So substitute negative 1 to variable x of the function. So we have f of negative 1 is equal to negative 1 squared plus 5 times negative 1 plus 6. Then simplify. So f of negative 1 is equal to 2. So since f of x exists, then the first condition is satisfied. Okay, for the second condition, we have the limit of f of x as x approaches to a exists. So our given function, we have f of x equal to x squared plus 5x plus 6. And we are going to find the limit of the function of this x squared plus 5x plus 6. So we're going to apply addition rule in finding the limits of the function. So this is equal to the limit of x squared, the first term, as x approaches to negative 1, and the limit of 5x as x approaches to negative 1. So this is the second term. Then the last one, the limit of 6 as x approaches to negative 1. So the limit of x squared as x approaches to negative 1, so this is equal to negative 1 squared plus the limit of 5x as x approaches to negative 1, this is equal to 5 times negative 1 plus the limit of 6, so this is equal to 6. Then we'll simplify. So negative 1 raised to 2 is equal to 1 plus 5 times negative 1 is negative 5 plus 6. So 1 minus 5 is negative 4 plus 6 is 2. Therefore, the limit of the function as x approaches to a is equal to 2. So since the limit of f of x as x approaches to a exists, then the second condition is satisfied. Okay, number 3, third condition. The limit of f of x as x approaches to a is equal to f of c. So the limit of f of x as x approaches to a is equal to 2 is 1, the solution, and f of c is equal to 2 also. This is the solution. Okay, so since the two values are equal, 2 is equal to 2, so then the third condition is satisfied. Since all of the three conditions were satisfied, then we can say that the functions f of x is equal to x squared plus 5x plus 6 is continuous at x is equal to negative 1. To illustrate that the function f of x is equal to x squared plus 5x plus 6 is continuous at x equal to negative 1, simply graph the function which includes the x value negative 1. So this is the graph of the function. So this is a parabola. And you will notice that the graph is continuous. So no more gap or holes on the graph. Okay? Example number 2. At x is equal to 3 is the function f of x is equal to x squared minus 9 all over x minus 3 continuous at that particular point. Show your solution. Okay, for the solution, again we are going to check whether the function will satisfy the three conditions for continuity at the given point x is equal to 3. So for the first condition, we are going to find the value of the function at x is equal to a. So the given here, so we have f of x is equal to x squared minus 9 all over x minus 3 at x is equal to 3. So next we are going to substitute 3 to variable x of the function. So we have f of 3 is equal to 3 raised to 2 minus 9 all over 3 minus 3. Then simplify. So 9 minus 9 is 0. 3 minus 3 is 0. So therefore, f of 3 is equal to 0 over 0. So this is indeterminate. So since f of x is indeterminate, then the first condition not satisfied. Okay, number 2. The limit of f of x as x approaches to a exists. So the given function is x squared minus 9 all over x minus 3. Then we are going to find the limit of the function as x approaches to e. So we have the limit of x squared minus 9 all over x minus 3 as x approaches to 3. Then factor out x squared minus 9. So this is equal to x plus 3 and x minus 3. Then simplify or cancel out x minus 3. So this is we can get x plus 3. So therefore, the limit of x plus 3 as x approaches to 3. So simplify this one. So we have 3 plus 3. So therefore, the limit of x squared minus 9 all over x minus 3 as x approaches to a or 3 is equal to 6. So since the limit of f of x as x approaches to a exists, then the second condition is satisfied. Okay, for the third condition, we have the limit of f of x as x approaches to a is equal to f of c. So the value of the limit of f of x as x approaches to a, so we got 6. So here's the solution. And for the f of c, we got indeterminate. Here's the solution because 0 over 0 is indeterminate. So since two of the conditions are not satisfied, the first and the third, then we can say that the function f of x is equal to x squared minus 9 all over x minus 3 is not continuous at x is equal to 3. To illustrate that the function f of x is equal to x squared minus 9 all over x minus 3 is not continuous at x equal to 3, so simply graph the function which includes the x value 3. So this is the graph of the function x squared minus 9 all over x minus 3. And you will notice that there's a hole on the graph. That's why it's not continuous at x is equal to 3. So when we solve the given function x squared minus 9 all over x minus 3 at x equal to 3, so we got 0 over 0, that is indeterminate. And that indeterminate represents hole on the graph, this one. So this is a removable discontinuity. Okay. For example number 3, determine if the function f of x is equal to 2 over x continuous at x equal to 0. So for the solution, step 1, evaluate the function f of x is equal to 2 over x at x is equal to 0. So we have f of 0 is equal to 2 over 0, substitute the variable x. So therefore, 2 over 0 or undefined. Okay, step 2, find the limit of 2 over x as x approaches to 0. So in finding the limits of this function, 2 over x, we are going to create two table of values. So in the first table, the x values here as x approaches 0 from the left, so we have negative 3, negative 1, negative 0.1 and so on. And for the second table, x values as x approaches 0 from the right, so we have 3, 1, 0.1 and so on. So to get the y values in the first table, let's say negative 3, So substitute negative 3 to variable x of the function 2 over x. So 2 over negative 3 is equal to negative 0.66 running decimal. And if x is negative 1, so this is equal to negative 2 because 2 over negative 1 is negative 2. Okay? If it is negative 0.1, so we have negative 20. If it is negative 0.0001, so we have negative 200,000. And if it is negative 0.000001, so we got negative 20 million. So you will notice that as x approaches to 0 from the left, what will happen to the values of y? So it approaches to negative infinity. So the limit of 2 over x as x approaches to 0 from the left is equal to negative infinity. How about on the second table? So we will get the y values. If the value of x is 3, so what will be the value of y? So substitute 3 to the variable x. So 2 over 3 is equal to 0.666 running decimal. If it is 1, the value of x, of course the value of y is 2. If it is 0.1, the value of y is 20. If it is 0.0001, so we have 200,000. If it is 0.00001, we have 20 million. Okay? So what will happen now to the values of y as x approaches 0 from the right? So it approaches to positive infinity. Therefore, the limit of 2 over x as x approaches to 0 from the right is equal to positive infinity. So the limit of the function 2 over x as x approaches to 0 from the left is negative infinity and is not equal to the limit of 2 over x as x approaches to 0 from the right is equal to positive infinity. So therefore, the limit of 2 over x as x approaches to 0 does not exist. Okay? For the step 3, observe that f of 0 is not equal to the limit of f of x as x approaches to 0. So since all three conditions were not satisfied, then we can say that the function f of x is equal to 2 over x is not continuous at x is equal to 0. So this is the graph of the function 2 over x. So this is a rational. So this one, the graph is not continuous at x equal to 0 due to the vertical asymptote. So this one, the dashed line. And this part of the graph is going positive infinity, while this one, this part of the graph is going to negative infinity. So this is an infinite discontinuity. Example of infinite discontinuity. Okay, let's proceed now to the continuity on an interval. So a function is said to be continuous at a closed interval a and b if its right endpoint, open interval, and left endpoint has no breakage, pulse, or discontinuity. So see figure below. So this is the figure. So this is the x-axis, the y-axis, and this is the graph of the function. Okay, so for the open interval, so we have AB, this one. So the symbol for open interval, we have close and open parentheses. We use close and open parentheses. For the closed interval AB, of course, we use the bracket. And this part is the right endpoint of A. Okay, and this part is the left endpoint of B. The following are the conditions needed to be satisfied to be able to know whether the function is continuous or not on a closed interval. So first condition, the function f of x needs to be continuous at an open interval a and b. Second, the function f of x needs to be continuous at the left endpoint a with these following conditions. So first, if f of a is defined. Second, if the limit of f of x as x approaches a from the right exists. And the last one, if f of a is equal to the limit of f of x as x approaches to a from the right. The third condition, the function f of x needs to be continuous at the right endpoint b. So with these following conditions. So if f of b is defined, and if the limit of f of x as x approaches to b from the left exists, and if f of b is equal to the limit of the function as x approaches to b from the left. Okay, let's have example number 4. Is the function f of x is equal to x squared plus 5x plus 6 is continuous on the closed interval -4, -1? Prove your answer by showing complete solution. Okay, let's have the solutions. For the step 1, the function f of x needs to be verified continuous at the open interval -4 and -1 by creating its table of values or simply knowing its restrictions with regards to its domain. Okay, let's have the table of values. We have the x values and y values. Okay, in finding the x values, we use the open interval -4 and -1. So therefore, we use greater than -4 but less than -1 for the x values. Okay, so we have this -3.9, -3, -2.5, -2, and -1.001. And let's find the y values. If x is equal to -3.9, so substitute -3.9 to variable x of the given functions. So we have -3.9 raised to 2 plus 5 times -3.9 plus 6. So this is equal to 1.71. If x is -3, so the y value is 0. If x is -2.5, the y value is -0.25. If x is -2, the y value is 0. And if it is -1.0001, the y value is 1.997001. Okay, based on the table, all domains or the x values in between -4 and -1 has its own defined y value. So therefore, we can say that it is continuous on the open interval -4 and -1. And another justification that this function is continuous on the open interval -4 and -1 is that all polynomial functions are continuous at every point or any interval x such that x is any element of real numbers. Okay, for the step 2, the function f of x needs to be continuous at the left endpoint -4. So for the first condition, evaluate the function f of x is equal to x squared plus 5x plus 6 at x is equal to -4. So just substitute -4 to variable x of the functions. So we have f of -4 is equal to -4 squared plus 5 times -4 plus 2. So this is equal to 2. Okay, for the second condition, find the limit of x squared plus 5x plus 6 as x approaches to -4 from the right. In finding the limits of the function x squared plus 5x plus 6 as x approaches to -4 from the right, so follow the addition rule. Okay, so we have the limit of x squared as x approaches to -4 from the right plus the limit of 5x as x approaches to negative 4 from the right, plus the limit of 6 as x approaches to negative 4 from the right. So this is equal to negative 4 squared plus 5 times negative 4 plus 6. So this is equal to 2. Then observe that f of negative 4 is equal to the limit of f of x as x approaches to negative 4 from the right. So we have 2 and 2. So 2 is equal to 2. For the step 3, the function f of x needs to be continuous at the right endpoint negative 1. So there are 3 conditions needed, same with step 2. So first condition, evaluate the function f of x is equal to x squared plus 5x plus 6 at x is equal to negative 1. So simply substitute negative 1 to variable x of the function f of x squared plus 5x plus 6. So therefore, f of negative 1 is equal to negative 1 squared plus 5 times negative 1 plus 6. So this is equal to 2. Second, find the limit of x squared plus 5x plus 6 as x approaches to negative 1 from the left. So just follow the addition rule in finding the limits of the functions. So we have the limit of x squared as x approaches to negative 1 from the left for the first term, plus for the second term, the limit of 5x as x approaches to negative 1 from the left, this one. And for the third term, plus the limit of 6, this one, as x approaches to negative 1 from the left. So this is equal to negative 1 squared plus 5 times negative 1 plus 6. So this is equal to 2. Okay? So we observe that the f of negative 1 is equal to the limit of f of x as x approaches to negative 1 from the left. So we have 2 is equal to 2. Okay? So since all the 3 conditions were satisfied, then we can say that the function f of x is equal to x squared plus 5x plus 6 is continuous on the closed interval negative 4 and negative 1. To illustrate the function, f of x is equal to x squared plus 5x plus 6 is continuous on the closed interval negative 4 and negative 1. So simply graph the function, which includes the x values from negative 4 to 1. Okay, so this is the graph of the function x squared plus 5x plus 6. And this one, the dark curve, continuous on the closed interval negative 4 and negative 1. Okay class, so that's all about the continuity of the functions. So if you have questions, clarifications regarding the topic, just comment on this video. Thank you for watching. God bless everyone.